Hello everyone. In this lecture, we will have a look at delete operation in binary search tree. As we remember from previous lectures, binary search tree has four common operations as insert data, that inserts data into binary search tree, search data, returns data element if it exists in binary search tree, and delete data, delete operation, the one that we will learn today, deletes the defined data element in binary search tree if it exists. And finally, we have three traversal methods for the next lecture as in-order, pre-order, and post-order. Delete operation has three cases, and those three cases are identified to keep binary search tree in valid form after a desired node is deleted. In case 1, if node to be deleted has no children. Case 2, if node to be deleted has one child. And case 3, if node to be deleted has two children. In the next slide, we will see in wider perspective how cases do work and involved when deleting a desired node. Just as a reminder, like in previous lectures, to have a valid tree, we need to have basic structure of a binary search tree that can be initialized like so. We have a root node, left and right subtrees, and data element that the data is stored in each node. For deleting a node, we can have a basic function that takes data element as an input argument and another function to pass the data to be deleted by looking from the root node as our starting node in our binary search tree. In the next slide, I will expand this implementation and make clearer statement on how deletion works in binary search tree. So let's assume from the given binary search tree, we would like to delete data element of 9, which also stands as our key value in our binary search tree. At the first condition, we basically comfort that our binary search tree is not empty and return null if it is empty before making any further executions in our method. At the second else-if check, we determine if data to be deleted is located at the left subtree of the root in our binary search tree. In this example, data element of 9 is smaller than the root node's data element of 10, so this condition would be executed. After execution, we would have our first recursion call where we change the root pointer to the root.left and assign the return value on the root.left when we return from this recursion. So here we can store the line number, root data element, and value of 9 in our method call. This way, we will know where we have left in this call. This will provide better understanding on how the deletion operation works in binary search tree for the given example. At the next function call, we know that our new root is now root.left, which is 7, and value is the same data element that we are looking at for deletion of that node in the given binary search tree. So we can store them in the new method call, or in other terms, in call stack. Again, root is not null, so we skip to the next if statement or else if statement and check if data is at the left subtree of 7, because we know that the left subtree of a node contains only nodes with keys lesser than the node's key. In our example, 9 is not smaller than 7, so we skip the condition, and at the next condition, we check this time if 9 is bigger than 7. 9 is bigger than 7. This means our key, which we want to delete, is located at the right subtree of 7. So let's store the values in this call method and have another recursion call, by this time taking right node of root node and pass it as root node at the next recursion. At this recursive call, we know that root is now 8 and data element we are looking for is 9. We basically do the same checks until we find that the root node value is same as the value that we are looking for. So again, same checks with this time root of 8 and value of 9. We skip the first else if statement and go to the right subtree of 8. Let's store the values in this method call and have another recursion. This time our root will point to 9 and our key value is also 9. We skip the first 3 statements since now we have equal data elements. This means we found the desired data element or key value to be deleted. So if this is the case, we have an else statement that will jump over 3 cases that we have mentioned in previous slide. The first case checks if data element or key value has no children. This can be found by having a simple if condition. If roots left and right is null, this means the data element to be deleted has no children. So basically, we point this root to null. As first if statement was executed, it will skip the next 2 conditions and return root. As we return from this method call, we can now see that we have left at line number 3 at the previous method call. At this call, root was 8, so we return our root and this way it will point to 8 now. Back to another previous method call. We have our root now stored as 7. We have executed line number 3, so we skip the next conditions and return our root. Last method call in our call stack, root is 10. We executed line number 1, so we do skip rest of conditions and return our root of 10. So now we have practically seen how a node is deleted in first case. The second case is very similar to the first case. We only need to have more recursions to keep the formation of binary search tree after deletion. So that's why we can try to delete a data element or key value which pursues the third case when node to be deleted has 2 children. In the given binary search tree, 15 has 2 children. So we can see how third case would be justified when we would attempt to delete the key value of 15 in our binary search tree. We input our data element and start from root as usual. Our binary search tree is not empty, so we skip to the next condition. Here, until we find the data element or key value to be deleted, we basically do the same recursions just like we did with the data element of 9. We can store the values in method call for better understanding and keep executing until we reach the point where we check the cases. In this case, we check if root has no children. To have first condition to be executed, both children of root should be null. In our case, it's not. So again, we skip. At the second condition, we check if one of child is null. In our example, both have value. So we skip to the else statement where we need to justify the case 3. At the third case, we create a predecessor node which we will use to reform our binary search tree after deletion of data element of 15. We need this because the node that we are going to delete still have 2 children which we need to relocate to keep valid binary search tree formation. We point the predecessor node to root's left maximum node. We do this because it will be the node that will be swapped after deletion of data element or key value of 15. So let's go over findMax method and see what it returns. In our example, root.left's right node is null. The if condition will be skipped and the root.left's value will be returned, which is 14. Additional swap method basically swaps root node with the predecessor node. To do this, we create a temporary value and take the data of predecessor node, which is 14. At next, we change the data of predecessor node to root node's data, which is 15. And use temp value now on root's node data to change the data element, or in other words, our key value. At the next line, we do our recursion again, which will be passing predecessor node and root.left as an update over root.left node in our binary search tree. At the next method call, root.left points to 15 and data is also 15. So we skip first if statement as our root is not null. We also skip next two else if statements as now both input arguments are same. After else, at the first if statement we check if our root.left and root.right is empty. Yes, they are both empty, so we point root to null, which will also point root.left from previous method call to null. As we return from this method call, we can pop it and go to previous method call. We have left previous method call at line number 12. At this call, we have left at root 14, so returning root will be pointing our root node to 14. So we pop from our call stack and go to line number 3 where root was pointing at 13. We have executed else if statement at this current block, so we skip and return root. After another pop, we now have root pointing to 10 at line number 3. Again, we have our other conditions skipped and root returned to 10. So now, I assume that you have better grasp on how delete operation works in binary search tree. In the next lecture, we will look at less complex implementation of 3 common traversals in binary search tree. But we finish here for this lecture. So thank you for your attention. Until next time.